Hello students. So this is the last topic of duality dual simplex method. So this dual simplex method was first developed by C.E. Lenke. He was the student of Charney. Okay, Charney has developed a method for resolution of these onlys. It is applicable to maximization as well as minimization problems. The constraints are converted into less than equal to type and the slack variables are added to set up the problem in standard form. That is, there is no need of artificial or slack variables. Whatever kind of constraints we have, we can, if some are of greater than equal to type, we will multiply them with the minus sign and we will convert them to less than equal to type. Okay. So initial simplex table is constructed if any vi is negative and the optimal condition is satisfied, then the given problem can be solved using dual simplex method. It eliminates the introduction of artificial variables because all the constraints are of less than equal to type. First, we select the variable to move out of the basis. This is opposite to that of regular simplex method. There we select the variable to enter into the basis first. The variable in the basis corresponding to the most negative value will move out of the basis. So in the basis, that is under column B, there will be some values, and out of those the values having means larger value in terms of negative sign, that variable will be selected. The variable corresponding to that value will be selected to move out of the basis. Okay, then we select the variable to enter into the basis, and it is determined based on this rule, this ratio, the variable corresponding to maximum of Zg minus Cj values divided by Arj will enter into the basis. So here Arj are the elements in the key row, that is a leaving variable row. Okay, the ratios of Zj minus Cj values with only those Arj's be taken which are negative only. So what we will do, we will consider only those Arj values which are negative, and for positive values or zero values we do not compute this ratio. And once we find out those ratios, we take the maximum of those ratios, and the variable corresponding to maximum will enter into the basis. Okay, let us understand this with the help of an example. Solve this problem using dual simplex method. So greater than equal to sign, less than equal to sign, less than equal to sign. What we have to do, we will convert all the constraints to less than equal to sign. Okay, so converting minimization type of objective function to maximization type. Yes, all the times when we apply simplex method, so I have told you that the objective function should be of maximization type. So converting this first maximization z dash is equal to minus 2x1 minus 2x2 minus 4x3, simply multiply by the sign, okay, to the right hand side, and minus of z dash. So this is here. Okay, now subject to the constraints. Okay, the first constraint was of greater than equal to type, multiplying this whole constraint by minus sign. So this is again convert greater than equal to type to less than equal to type constraint by multiplying the minus sign. So this is again converted into less than equal to type. Now I have all the constraints less than equal to type and maximization type. I can simply introduce slack variables and get the standard form like this. This you know already, that how do we find the standard form. Okay, all these variables are equal to 0. So setting x1, x2, x3 equal to 0, we get from standard form s1 equal to minus 2, s2 equal to 3, s3 equal to 5. So this is my initial basic solution. After that we construct a table as usual. Okay, CB basic variables, value of basic variable x1, x2, x3, s1, s2, x3. So all this we write as usual. Slack these are the basic variables as slack variable, s1, s2, s3. Their options are 0 in the objective function. Their values are minus 2, 3, 1. And all these values as usual we find from the standard form. Sorry. and we find out ZG values, that ZG minus CG, all these are positive. So the objective, this solution is optimal initially, and we can see here the values of the slack variables are all not positive. So this is infeasible solution because this value is less than or equal to 0. So yes, now we can apply this dual simplex method. Since S1 has negative sign, here I have explained S equal to -2 and all the minus equal to 0. The solution is optimal but infeasible. First, we determine the variable moving out of the basis. That variable will move out of the basis which has most negative value. Here S1 has most negative value, so it will move out of the basis. Next, we determine the variable entering into the basis. To do this, we find ratios of elements of Zj minus C0 to the elements of key row. Neglect the ratios corresponding to positive or 0 elements of key row. The desired ratios are now like this: 2 upon -2, 2 upon -3, 4 upon 5. So we can see from here 2 upon -2, 2 upon -3, and 4 upon -5. So 0 upon 1, 0 upon 0, and 0 upon 0. We don't consider these ratios with positive and 0 elements. Okay, so these are my ratios, and here I have simplified form. I have written like this: -1, -2 by 3, -4 by 5, and out of these, which one is maximum? -2 by 3 is maximum among all these. This is more nearer to 0. Okay, so the variable corresponding to this maximum ratio will enter into the basis. In this case, x2 will enter the basis. Okay, so what we have done now, we have determined the variable moving out of the basis and variable moving into or moving in or entering the basis. After that, we change all these rows of the table by using the same technique. Okay, the new key row will be obtained by dividing all the elements of key row by key elements. So divide all these by -3, and these are the old rows, second, old row, third. So new row, second, new row, third can simply be obtained by using the formula that old row minus element in front of the key element multiplied by the new key row. So same formula we apply and we convert these rows into new rows, and here we get a new table like this. Okay, and again what we do, we check with the values of yes, these yes, I have written here the this values, v values, values of the basic variable 2 by 3, 7 by 3, 7, 5, 3. And again, if we find the Zj minus Cj values, these are positive. The Zj minus Cj values are positive, as well as all the slack basic variables are positive. Hence, the solution is optimal, feasible. Okay, and we stop here. Okay, so by mistake I have written b here. Normally we used to write b values here, so there is no problem if we write here or here, no problem. Okay, so now all the bi's are positive and all Zj minus Cj greater than or equal to 0. Therefore the optimal solution has been reached at, hence the optimal solution is x2 is equal to 2 by 3. We can see here, and other values are 0, so x1 is equal to 0, x3 is equal to 0. Maximize z dash is equal to this minus 4 by 3, but original problem is of minimization type. Minimize z is equal to minus of maximize z dash, that is minus of minus 4 by 3, 4 by 3. So this is my answer now. So this is how we find the solution by dual simplex method. Thank you.